Okay, and I've already made the announcements to two of you, so don't need to do those again unless you've forgotten them already. No, okay. You will remember not to come on Monday, right? Promise? Okay. All right. Okay. All right, sorry, let me get set up from current slide. And we'll get projections soon. It's coming into focus here. Now, my memory is we are in Chapter 1, Introduction to Differential Equations, and 1.1 is Definitions and Terminology, and boy, do they ever draw this out. Okay. Now, okay, again, it's definitions and terminology. Example 6, that's where I think we're picking up today, is that right? Example 6, or past that? Example 6, bottom of page 7. We did something very, very similar to this last time, talking about it, but this is making one little additional distinction than what we probably did last time. Here we have a function, okay? The function is, let me get my pen set up. The function is y is equal to 1 over x. I think we talked about this, right? Some of the points on this would be 1, 1, 2, 1 half, 1 half, 2, 3, 1/3, 1/3, 3, and on and on and on. So it gets in closer and closer, approaching the y-axis as a vertical asymptote, approaching the x-axis as a horizontal asymptote. But also negative 1, negative 1, negative 1 half, 2, negative 2, 1 half, negative 1 half, negative 1/3, 3, negative 3, 1/3, negative 1/3, and so on and so on and so on. Okay? So again, approaching the x-axis as a horizontal asymptote, the y-axis as a vertical asymptote. Now this is the function. The domain of the function is all x not equal to 0. Okay? The function can be drawn like this. You just don't have a value there. If you wanted to, you could draw a vertical asymptote there along the y-axis, and you could draw a horizontal asymptote on the x-axis. That doesn't matter. The function is everywhere, defined everywhere in its domain. It's everywhere except x equals 0. Okay. Now, if you wound up with a solution of y is equal to 1 over x, this is the function. Here is the solution of y equal 1 over x. Okay? Solutions always come in an interval. And I think we talked about this before. The interval can be anywhere that doesn't contain a discontinuity. Okay? Or somewhere it can't do. So the interval can be from -7 to -3. It could be from 1 to positive infinity. It just couldn't be both parts of that function. It can't happen because if you try to include both parts, you cross over with discontinuity. You can't do that. Your your solution always is accompanied by an interval. Okay? Got to. So that, I think, is the purpose of this. And they do go a little bit further. If y is equal to 1 over x is a solution of the linear first-order differential equation xy prime plus y equals 0. Now, the first thing they want you to do is verify that indeed is a solution. How would you do that? Say that again?
Differentiate on y.
Okay. Yeah, the derivative of y prime is what? Negative 1 over x squared. So let's plug that in here and see what we get. X times minus 1 over x squared plus 1 over x. The question is that equal to 0? Well, one of these x's takes one of those out, or that x takes that one out, and you have minus 1 over x plus 1 over x is equal to 0. Sure enough, that is a solution. Okay? It is a solution. Now, you can say that is a solution, but you also have to give on what interval. Okay? And in fact, they say, you could say it's a solution from minus 3 to minus 1. Sure, that would be a solution there. It would be a solution from 1/2 to 10. Yes, that would be perfectly fine. Okay? You could say a solution from negative infinity to 0, as long as both of those have parentheses around them. If that second one had a bracket, not. Or even from 0 to positive infinity, as long as those are parentheses. Okay? So you always, with a solution, have to give your interval of solution. Okay. Now, that said, let's move on. Any questions on that? Let's move on to explicit and implicit solutions. Now, this is pretty similar to, let's see, I don't want to do that. I just want to go to another page. Okay. When you were talking about explicit and implicit functions, especially when you were, let's see, what was that? Goodness, we did it back. I know, I'm wanting to say Cal 1. I just can't remember exactly where it was. When you, if you were able to solve it exactly from what you were given, it's an explicit function. If you had to do some wiggling and manipulating of it to get there, that then could have been an implicit function. That's a really lousy way to do it. But a solution in which the dependent variable is expressed solely in terms of the independent variable, that's an explicit solution. Okay, let's get that down. A solution in which the dependent variable is expressed solely in terms of the independent variable that's said to be independent variable and constants, I guess, and constants. That's said to be an explicit solution. Okay. For our purposes, let's think of an explicit solution as an explicit function that you just have y is some function of x. Well, they love using phi for some reason. That's fine. That we can manipulate, evaluate, and differentiate using standard rules. Okay? Here's a couple. Remember, probably the last time we probably did one that was y is equal to 1/16 x to the 4th. That's an explicit solution. The dependent variable is expressed solely in terms of the independent variable with constants. Okay? We also did one, y is equal to x e to the x. Y is isolated, expressed solely in terms of the dependent variable, solely in terms of independent variable. Okay? Y is equal to 1 over x, the one we just did. The dependent variable y is expressed solely in terms of constants and the independent variable x. Okay? Now, this is a solution for the differential equation dy dx is equal to xy to the 1/2. We did that last time, I'm pretty sure. This one was a solution to y double prime minus 2y prime plus y is equal to 0. I'm pretty sure we did that one last time. And this one we did today, that xy prime plus y equals 0. We just did it a few minutes ago. This is a solution for that one. Okay? So those are all expressed explicitly. Okay? Now, if you remember, we also said y equals 0 is a solution for this one. Okay? Because y certainly can be 0, the square root of 0 is 0, the first root of the 0 is 0. Yeah, that works. Y is equal to 0 certainly works there too. And say y is equal to 0 is an explicit solution of the third one. I don't buy that, because y will never be 0. Okay? Well, wait, okay. Not according to this, but y equals 0 will fit the bill there, because the derivative of if y is equal to 0, derivative of y is equal to 0, and x times 0 plus 0 is 0. But that doesn't come from here. These two can come from there. Plug in y equals 0 here. When x equals 0, y is equal to 0. When x equals 0 here, y is equal to 0. When x equals 0 there, y is not equal to 0 there. But there's no x you can plug in there to make y equal 0. So these two trivial solutions come from the given solution. This trivial solution does not come from that one. It's a separate issue. Now, I don't think they're making a big deal about that, but anyway. Here is your definition then of an implicit solution. Okay? And it's not just one that's not explicit. Okay? Here's what it is. Implicit solution of an ordinary differential equation. ODE, ordinary differential equation. A relation g of x, y is equal to 0 is said to be an implicit solution okay, of an ordinary differential equation, ODE, on some interval I, provided there exists at least one function v that satisfies the relation as well as the differential equation. Boy, That came out strange, didn't it? That was supposed to have been a phi, and it didn't look anything like a phi. At least one function phi. I was writing and not looking, and I think my thing wobbled on me and I got completely off. Okay? Function phi that satisfies the relation as well as the differential equation on I. Okay. Now, almost sounds like a bunch of weasel words. Let's see if we can make any sense of it. The relation g of x, y is equal to 0 is an implicit solution of an ordinary differential equation on I, provided that there exists at least one function phi that satisfies the relation as well as the differential equation. Okay. Now, here's the deal. This g of xy may have x's and y's in it. The explicit solution, y is equal to some function of x. Only functions of x. This one may have x's and y's in it, and if that satisfies the relation here and also the differential equation, then it'll be a solution. Okay? It may have x's and y's in it. That's the difference. Okay? Notice the may there. It doesn't have to, but it may. All right. Let's look at example 7 and see if we can make any sense out of what they're talking about. Here's a relation. X squared plus y squared is equal to 25. Now, why do they call that a relation and not a function? I saw your hand do it. Yeah. This is a circle. Is that a function? No, because it fails the vertical line test in certain places. Okay? So therefore, it's not a function. It is a relation. But it is an implicit solution of this differential equation. dy dx is equal to minus x over y. Okay? Now, let's verify that it is a solution. Let's take the derivative of this thing. Now, how do we take the derivative of that? The easiest way is implicitly. This is where I first recall running into implicit. The term implicit is when you're taking the derivative implicitly. So how do you take the derivative of this? It's the derivative of x squared. 2x plus, what's it? Okay, say again. 2y. Okay, wait. You have to have a y prime in there. Is equal to 0. Okay? Why? Because y is a function of x. X isn't a function of x. That's why you can just say 2x. You're done. But y is a function of x, so you have to do the chain rule. The outer function is the squaring function, 2 times y, and then the inner function is y. That's where you do your y prime. Okay? Now, let's solve for y prime, and what do we get? Subtract 2x from both sides, and you get 2y prime is equal to minus 2x. Okay? And divide both sides by 2y. And that gives you y prime is equal to 2's go out minus x over y. Okay? Y prime. Okay. And y prime is your dy dx. So yeah, we've shown that that relation certainly satisfies itself and it satisfies the differential equation. So that's an implicit solution. Okay? Now, the other way of telling that is that here you have your derivative, for instance, cannot be written just as a function of x alone. You got the y's in there as well. Okay. Now, another way you could have done this, if you had wanted to solve it explicitly, you could have solved this equation here for y. And that would be y squared is equal to 25 minus x squared. And taking a square root of both sides of that, what do you get? Yuck. Let the pen touch the page there, I didn't realize it. To erase something, and it must have double-clicked or something. All right, let me get back to the pen. Okay, now we're there. Do what? Square root of both sides, and what does that give you? Plus or minus the square root of 25 minus x squared. And here is where we see it's not an equation, because you have a plus and you have a minus. Now you can take either one of those separately and it would be an equation. Second?
You say equation or function?
A function, yeah, I'm sorry. I should have been saying a function. That would be a function, or that would be a function. But they both have to be functions, because then you have two possible, you got the same y, I'm saying this right. For any x, you can get two possible y's. You get a plus or a minus. So that's not a function itself, but either half of that is a function. Top or bottom half. Okay. Now, I think that's all we have to add. I don't like drawing the graphs, but this time I will. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Here is a circle. You supposedly, just imagine that's a circle. Okay? Or 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay? That would be as, I'm sorry, I just drew the same thing I did before. Okay. This would be a function. I'm not going to tick all the points. That would be a function. That's not a very good looking semicircle. But either one of those is this. This relation here would be a solution to any one of those, but I guess you have to say it, but it's usually a good practice to say this is a solution where x is anywhere from -5 to +5, or -5 to 0, or 3 to 1, or -3 to 1, or something like that. This is basically your implicit solution, because that's a relation. And this would be an explicit. Yuck. Okay, now, both of these are explicit solutions. You can only do one at a time. That's your implicit solution. Next sort of topic here is families of solutions. We'll be seeing these a lot, so kind of get used to them. They're pain in the neck to draw sometimes, or to illustrate, because generally they come in infinite numbers of them, so you can't illustrate them all, you just have to do a select few. So the study of differential equations is similar to that of integral calculus when evaluating an antiderivative or indefinite integral in calculus. Sorry about losing my throat here. We can use a single constant of integration. Constant of integration. Analogously, we'll see in chapter 2 that we use a constant C of integration, we'll start getting more and more that when solving for first order differential equations, and they write these in a couple of different ways. I hope you remember this, the general equation and the, I can't remember how they classify them, but when you write a first order differential equation like this, f as a function of x, the independent variable, y, the dependent variable, and then y prime and as many others as you might have, this is first order, equals 0. That's one way to express a differential equation, okay? Another would be, say some little f of x and y would be equal to y prime. That would be another way to express it. Now, we usually obtain a solution containing a single constant or parameter c if it's a first order differential equation. If it's second order, you need 2. Third order, 3. They keep going up like that. But for a first order differential equation, you usually will only need one one parameter usually will define everything that you need. Okay. So if a solution of a differential equation contains a constant c, let's spell this out. Okay. A solution of this differential equation, linear, well, okay, I'm sorry, not necessarily linear. Just a first order differential equation, okay? We can usually when you got a solution for a differential equation like that, it usually obtains a solution containing a single variable. Now they sort of italicize usually, okay? Okay, we usually obtain a solution containing a single constant or parameter. Sorry. Okay. Now, if you have that single constant in there, your solution set will then look like this. G of x, y, and some combination of that constant c is equal to 0. Okay? Because that c is specific to the solution set. Okay. That is then called a one-parameter family of solutions. My writing stinks. A one-parameter family of solutions. Okay. If you're solving in nth order, oh no, hit the wrong button. Okay, well, never mind. When solving an nth order, okay, do they specify? They don't say ordinary, but we are going to deal with that. ODE. The book doesn't say ordinary, but that we're going to deal with that. All right. And that nth order differential equation can be written like this. Capital F as a function of x, y, y prime, y double prime, y triple prime, dot, 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 up to and including y sub n minus 1 prime. Okay? No, I'm sorry, n. The nth derivative. Okay. And that equals 0, then we seek an nth order. I'm sorry. An m parameter. Okay, I was getting my orders and parameters crossed up. An m parameter system of solutions. Okay. So in other words, first order, you got to have at least one constant, which is your parameter. Okay. If you have a seventh order differential equation, you're going to have 7 parameters, at least, okay? And so you seek that n parameter system of solutions. In this case, that would be g of x, y, y prime, y double prime, y triple prime, all the way up to y to n minus 1. Okay. Oh, I'm sorry. They're changing things around on us now. I'm sorry. All right, I messed up. I got carried away with my primes again. Okay. You're looking for parameters now. And this g is a function of x, y, but then c1, c2, C3 ... up to including to C sub n minus 1. Now that's where the n minus, no? That's right. You need n of them. Okay, I'm sorry, I got that crossed up. And here's why. Your y is still in the picture. If you had pulled that out and made that a c, then you actually have c plus 1. But your y is still in there, and you have to have n parameters to match each one of your derivatives here. One first order differential equation, one parameter. Second order 2, third order 3, so nth order needs n parameters system to satisfy it. Okay. Now, that means that a single differential equation can possess an infinite number of solutions corresponding to an unlimited number of choices for the parameters. Okay? A single differential equation can possess an infinite number of solutions corresponding to an unlimited number of choices of parameters. A solution of a differential equation that is free of parameters, you can also have, I think we've mentioned this before, a solution of a differential equation okay, this is going blank on me, okay, that is free of parameters okay, is called a particular solution. Okay, now we're not going to run into this, well, we probably will in the next example, but all that frequently until we get to what they call the non-homogeneous case. Then you have some very specific particular solutions. Let's not worry about that now. But we've already run into this sometime. Remember when we had the trivial case? Y is equal to 0? No parameters in that. Okay, so that is a particular solution. That's a really dumb and special case, but it is one. Okay. The parameters in that set, G here, are in many ways arbitrary, at least up to a point. They're arbitrary in the fact that it's not the only set of parameters you could have, okay? But they're not arbitrary to the point that you say, you can put any number in there. No. They have to satisfy the differential equation, but if you make one assumption one place, then it could change the parameters somewhere else. I know this sounds really almost mystical, you know, but don't sweat it. It'll start making more sense later, okay? Here is a relation similar to one we had before. X squared plus y squared is equal to c. Okay, now that is a parameter, c, okay, and it satisfies the same equation we had before, dy dx is equal to minus x over y. Okay, because this is an equation of a circle of, yes ma'am? Okay, I'm sorry?
I didn't realize you were in class. I take you from Math 125.
Right.
The independence study.
Right. Okay. Now, in the email I sent, did you get it?
Yes, I did.
Okay. If you remember, Wednesdays, I have almost no office hours on Wednesday. I have 8 to 10 in the morning, and then a little chunk around lunch, but then nothing else because I have to go to the Birmingham campus for a class this evening. Have you got a specific question, or is it sort of broad?
It's sort of broad. I didn't see any of the work, but I did find the YouTube channel
Okay.
and wasn't really sure what to do from
Okay.
there.
Okay, did you see Blackboard was all set up?
It is set up,
Yeah.
and the assignments are set up as well.
The what?
The assignments are
Okay,
set up as well.
when you watch the YouTube videos, do you have a book?
Yes, I have the book.
Okay, now what book do you have?
The Larson book.
The what?
The book you had. I have that exact book.
Okay, the Larson, but there's two Larson books. One says, I don't have it in here with
I
me.
have the book. They were on the syllabus, right?
Yeah, okay. Now the one on the syllabus, that's the one you need. The 11th edition.
Yes.
You have that? Yes. Okay. So I teach from that. You can follow the YouTube videos from that. But then when we finish a section or finish a class, then I tell you what problems to do in the book.
Okay.
So they're all in the YouTube videos.
Oh, okay.
Yeah. Okay?
So that works. Thank you.
Okay, surely. And let me get your name.
McQueen, B.A.
Okay. I'll get that. I'll mark you as present. Now I'll be free tonight after 6:30 on the Birmingham East Campus in the nursing building on the first floor in room 103. If you have any further questions, I can get with you then.
Okay, it'll probably be Friday morning.
Friday morning, I'll be on Birmingham West Campus.
Yes.
Okay. All right. Sorry about that. How much? No. We go to 3:45, right? Yeah. Okay. So we got some time. I should have turned off the recorder. I forgot to. So all that'll be on the recorder. Okay. Here's just a dumb example. Okay. This is a one parameter system. There's a C. Now, the C is pretty arbitrary, as they said, up to a point. What C could you not put in there?
You can't put 0, just a point.
Yeah, 0 would just give you a single point. That would be okay. That would not be very interesting, but be okay.
But you can't do like it.
It cannot be negative, because then there's no way you can x squared plus y squared is equal to negative 45. You know, it just can't happen. Not in the real number system. We're going to say in the real number system. So you see, that's why they say C is somewhat arbitrary, but not completely arbitrary. There are sometimes values you just can't have, you know. Other times it could be just about anything. Okay. This is sort of nitpicky. Let's see if example 8 makes a little more sense. Okay. Let me clear my ink on this slide and move to this one. Okay. Example 8. For all real numbers C, okay, now that sounds like it's very arbitrary. The one parameter system okay, y is equal to cx minus x cosine x is an explicit solution of the linear first order equation. Xy prime minus y is equal to x squared sine x. Okay. Now, on minus infinity to infinity. Everywhere in the real number system. Okay. Now, we've hit this a few times before, and I'm going to emphasize it here. This section especially, but most of the first chapter is mostly spent having you verify something. They're not telling you how they got that solution. They just say verify it as a solution. So get used to it. That's what you're going to be doing most of this chapter, is verifying solutions, not how to find the solution. Seems like they really run this into the ground, but let's do it. How do we verify that?
You gotta find out y prime first.
Yes, you do. So let's do y prime is equal to? Help me. C, not cx, C, right?
C minus.
Okay, C, oh, minus. Okay, I'm sorry. Minus what? C minus,
What's the sign of, minus?
okay.
The sign of x. C minus the sign of x.
Okay, not quite. Okay. You either, okay, this is a product rule, right?
Only this.
Okay, so it'd be C minus derivative of the first, which is 1, times cosine x, then minus from that sign times, okay, it's going to turn out being a plus x sine x, okay? I went on and did it, okay, because the derivative of this would be c, and the derivative of this, let's do, just forget about the minus sign, okay? Derivative of that is the first times derivative of the second, which would be, well, okay, let's do the derivative of this times that would be this, so it's minus that, and then the second part is this times the derivative of that. The derivative of that is minus sign, so you have minus and minus is plus x sine x, right? Okay. So that's your first derivative. Now, let's see if that makes it work. X times the first derivative, which would be c minus cosine x plus x sine x, minus y, which is cx minus x cosine x. The question is that equal to x squared sine x? Somehow it doesn't look like it would be, but looks like it could be. So let's multiply through here. This gives you cx minus x cosine x plus x squared sine x, right? Then distribute the minus sign across, minus cx plus x cosine x. Is that equal to x squared sine x? Okay, well here we have a cx minus cx, those add to 0. Here we have a x cosine x minus x cosine x plus x cosine x, they add to 0, and sure enough, x squared sine x is equal to x squared sine x. So sure enough, this single parameter solution, solution, single parameter solution, satisfies that differential equation. Okay. And it does it for all values, x, anywhere from minus infinity to positive infinity. Yes, sir. I'm sorry?
I hate to interrupt, just got a quick question.
Okay, what's that? Yeah, okay.
This ain't no big guy, I didn't take the test, I couldn't.
Right, okay. All right, thanks.
Thank you.
Is there a sign out here that says, bother this class? Ooh, I recorded that. Okay.
Oh, no one else is seeing it.
No. Y'all probably won't either, will you? Okay, never mind. Okay. Now, so we found out this is a solution, an explicit solution, y is equal to all functions of x, of this first-order differential equation. Now notice we keep saying a solution or an explicit solution. We're not saying it's the only one, but it is one, okay? Well, it's many because C is arbitrary, okay? And it says for all real numbers C that will work. Now, and I sort of hate the way they word this because but it's a correct wording. But it says, and I don't want to draw it, is my problem here. So I'm just going to hold it up. Sorry, Corey listening at home or whoever. No, I'm sorry, Corey's not in this one. Is he? Yeah, he is. Okay, sorry, you won't be able to see it, but if you've got a book, it's on page 9. Okay, this is a series of graphs of various C's. The blue graph here is when C is equal to 0. Okay, the red here that starts out low and then winds up high, that's for positive C. C is greater than 0. The green down here that starts high but then winds up low, that's for C's less than 0. Okay? The ones in between there, like the one above the red, that would be an even more positive C. The one here, the yellow, would be in between 0 and whatever this C was. So that's what one family of solutions would look like. Now, if you knew a particular value, and obviously 0, 0 won't work, because all of them pass through 0, 0. But any other value other than 0, 0, and sure enough, you're going to find you'll be on one of those lines. Maybe not these lines, but one that would be in between. So that's sort of what this is getting at now. Every C you choose is going to give you a different curve, but if you knew one particular value, you could determine which C you want to use. Now, the solution y is equal to minus x cosine x, if you'll notice, that's when C is equal to 0. So that would be the blue solution here. That would be the one you would use for C equals 0. Because you see, that term doesn't have it. Now, what do we have there? Y is equal to minus x cosine x. That's a solution free of parameters. So that's one definition of a particular solution. Okay? Remember, a particular solution was a solution without any parameters in it. Okay? This one came from our one parameter system. Other times we'll have ones that don't come from there that will be particular solutions. Okay? Now, just like we were saying before, if you had an nth order differential equation, you're going to need n parameters. Okay, so now we'll do a two-parameter system. Here's y is equal to c1 e to the x plus c2 x e to the x. Okay? That's an explicit solution of this differential equation. Y double prime minus 2y prime plus y is equal to 0. Now, I think we had this one much earlier. Yeah, it was part B of example 5. But we need to verify it. See, this is, from now on, they're going to be saying just about every time, verify. So what do we have to do to verify this one? Take a derivative. So y prime would be Second?
C1
C1 e to the x, perfect.
C2 e to the x
Plus C2 e to the x, perfect. Plus C2
e to the x.
x e to the x, isn't it?
Oh, yes, I thought I already said that.
Right?
Yes, that's.
Okay. All right. That's your y prime, but we also have to go one more and do a y double prime. And what would that be? C1 e to the x
C2
plus C2 e to the x
plus C2
plus C2
e to the x
e to the x
plus C2
plus C2
x e to the
x e to the x. Very good. And we can combine these two like terms here and have C1 e to the x plus 2C2 e to the x plus C2 x e to the x. All right. Now let's take that y double prime and plug it in here. Don't stretch out a bit here. C1 e to the x plus 2C2 e to the x plus C2x e to the x minus 2 times y prime. Y prime was C1 e to the x plus C2 e to the x plus C2x e to the x. Right? Plus y, and your y was C1 e to the x plus C2x e to the x. Right? The question is that equal to 0? That's what we need to determine. Well, what we need to do is clear that parentheses, so let's do it. C1 e to the x plus 2C2 e to the x plus C2x e to the x minus 2C1 e to the x minus 2C2 e to the x minus 2C2x e to the x plus C1 e to the x plus C2x e to the x. Is that equal to 0? Oh my word. Let's see. All right.
Take
Yeah.
me a good minute to write this down.
Okay.
I'm still following you.
All right. Well, here's a C1 e to the x, and we'll combine it with minus 2C1 e to the x. That gives you a minus C1 e to the x. And then here's a plus C1 e to the x, so that wipes that one out. So those go away. Okay? Well, here we have 2C2 e to the x minus 2C2 e to the x, so those go away. And here we have a C2x e to the x plus another C2x e to the x, but then a minus 2 C2x e to the x. Yes, so those go away too, and we're left with 0 equals 0. So yeah, we have verified that that two-parameter system is a solution to that differential equation. Now, we haven't figured out how they got it, but we do know it is one. Okay? Now, here is similar to before. Sorry, Corey, I'm not going to graph these. Here are some solutions of this differential equation from 8b, part B of example 8. Now, they don't list which ones are which, but for different values, they do. Here's some, okay? The red curve here, see the one that comes down like this? That's the one when you choose C1 is equal to 0 and C2 is equal to 5. So then you would have, where is it? Right here. 5x e to the x. That would be this red curve here. And that's a solution. When you do C1 equal 3 and C2 equals 0, that gives you y is equal to 3 e to the x. Well, that's the green solution. And there's the green solution. Yeah, that's just an exponential equation. Y is equal to 3e to the x. Okay? The blue one here is when you have C1 equal 5 and C2 equal 2. So you'd have 5e to the x plus 2, oh no, minus 2. Where did they get the minus sign there? I don't, okay, something's wrong here with this picture. I haven't figured out which one it is. Either the C2 is a minus 2 or that's a plus. I don't know which it's supposed to be, and I'm not about to try to figure it out. I think that would be a minus 2. So C2 has to be a minus 2. That would be the blue curve. So they left off the minus sign of that. But anyway, those, and then there's the other black ones are just other values for C1 and C2 that you can put in there and come up with all sorts of different solutions. The more parameters you have, the more choices you have, and the more tangled the web could be. Okay, but it's just showing you have an infinite number of solutions. Okay. All right. Now, with all that under our belt, remember a particular solution is one without a parameter. So any of those that we plugged in parameters, that became a particular solution for a particular problem. However, sometimes a differential equation possesses a solution that is not a member of the family of solutions of the equation. That is a solution that cannot be obtained by specializing any of the parameters in the family of solutions. Such extra solution is called a singular solution. Okay? A solution to a differential equation that is not a member of a family of solution and families of solution depend on the C's, the parameters, okay? But one that is not, it is a solution, but doesn't depend on those. These extra solutions are called singular. I'm abbreviation like crazy. Singular solution. Now, singular may sound like there's only one of them. It's not saying there's only one. It's just called, it's different from the others. Okay? Now, have we got time? Maybe. We've seen this one over and over again. Y is equal to 1/16 x to the 4th. And y is equal to 0. Well, that would happen when x is equal to 0. Okay? These are solutions of this differential equation. dy dx is equal to 1/16 x to the 4th. No. X, y to the 1/2. Okay. We've already seen that. Okay. We did it in section 2.2, blah, blah, blah. Oh, I'm sorry. We did it earlier today even, okay? And that's true on minus infinity to infinity, everywhere for all values of x, okay? Now, that's the case. Later in 2.2, we're going to actually solve this differential equation, okay? We'll learn how to solve it there, and we'll actually solve it, and we'll find that solutions are this one parameter system, because you have one, it's a first derivative, so it's a one parameter system. Y is equal to 1/4 x squared plus c squared, okay? Now, when c is equal to 0, okay, then you have 1/16 x to the 4th, right? That comes directly from that, right? When c is equal to 0, okay? Oh, wait. Now, this solution is only good for c's greater than or equal to 0. So it works for 0, but it doesn't work for negative c's, okay? But notice, since the trivial solution, which would be okay if you plugged in x equals 0, but the trivial solution doesn't fit this form at all. So when we came up with this form, yeah, this one works, it fits it nicely. But how can you get y equals 0 out of that? Because there's no way of assigning a value for the constant c that's always going to give you y is equal to 0. So that will be, turns out being a singular solution, okay? Because you can't get it from the single parameter system, okay? Now, I'm fearful we're not going to be able to do example 9 in the time we got left. What do you think? Probably not.
2 minutes.
Huh?
2 minutes. Oh,
2 minutes. I don't think we'll do it, so we'll start with example 9 next time. Let me erase what I have here. All right. We're almost through at 1.1, and you'll be very glad when we are, won't you? Okay? Homework exercises here would include any of the odds that are in the back of the book, 1 through 7, 9 if it's in the back of the book, 11 or 13 if they're in the back of the book. I think you could do 15 or 17 if they're in the back. Believe you can do 19 if it's in the back. Think you can do either 21 or 23 if they're in the back. I think you can do either 25 or 27 if they're in the back. Believe you can do 29 if it's in the back. I believe 31 or 33 if they're in the back, and I think 35 if it's in the back. I think the rest of those maybe we'll need to wait until we do those last couple of examples before you can get to those. So try try those. And we'll pick up at example 9 on page 10 next time. Sorry we didn't get any further. I think if we hadn't had those 2 interruptions, perhaps we would have gotten there. All right. I just can't believe it happened twice. Walk in. Oh, are you in class? No, we're just sitting here.
Yeah, you're just talking